Yes, did Marie reply the email about the intersection? I sent her the information, so you should be okay.
Today is the
The
last day.
deadline, talk to Maria.
Okay.
Okay, go to the, the main office?
Yes.
Yeah, talk to her, okay?
Thank you.
The paycheck is going to be late because we put it in late, but for the, yeah.
Okay, I can talk to her. Thank you.
Okay.
Well, if you're just CEO. Oh, okay. You're fine. Yeah, they're kind of, they kind of do some classes. I was doing shopping. Self-driving. JT, what on that garbage?
All right, let's start. Good. Time to start. Please. Hello? Welcome back. Okay. First, a couple of announcements. One, I had posted the first homework. It's due 1 week from today. Okay. It's available in Blackboard, paper and pencil, and individual. Okay. And it can be turned in through Blackboard. The second announcement is that unfortunately I have to cancel my office hours today because I'm traveling to DC. I'm leaving to the airport after class. So I will be back here in time for Friday office hours. In the meantime, you can contact Gwen, the TA, for questions or send me emails if you have questions. Okay? All right. Any questions from last class? Yes?
Sorry, just about is the homework teamwork or individual?
No, the homework, the written homework is individual, okay? What will be in teams is the projects, okay, the computer projects. And that reminds me that if you need to find a partner for the project, you can post in Piazza asking for people that are looking for partners, okay? So that's a good way of communicating, especially for the people that are not in class. But for everybody in general, that's a good way of finding who is looking for a partner. Okay. Any other questions from last time? No? Okay, so just as a reminder, this is the grading policy for the class. Okay, so the written assignments is worth 10% of the grade. Again, these problems, is very important that you attempt to do it and you try your best to do it because they really prepare you for the exams. Okay, for both the midterms and the final. And the exams is a significant chunk of your grade, right? So the midterms is 30%, we have 2, and the finals another 30%. Okay. And again, there will be the possibility of doing an extra credit project that is due basically the last day of the semester. Okay, I will be posting topics for that extra credit project later on in the semester, closer to the exams. That project is individual too. Okay, so that one you cannot force your partner to do it with you. It's just an individual choice. Okay. All right. Okay, so last time I introduced to you the concept of images and that there are different kinds of images, right? Depending on what kind of radiation and what type of sensor we're using, they measure different things. So the ones that we're more used to look at are images that work with reflected light, and that's what we call photos. That's the kind of pictures that we take with our cell phones. Okay. There's also distance images. We call them range images. And those are, for example, images that you can take with a Kinect. Okay. And we have also medical images that they basically measure density of tissue, like tomographies. And in that case, the numbers and the pixels in those images actually represent how dense the material that's being radiated is. Okay. And we also have images that are sensitive to heat. And those are good, for example, for taking images at nighttime when there is no light. Okay. Again, in our class, we will be talking a lot on regular images or intensity images. Sometimes we might talk about range images, but mostly we will stay in this domain. Okay. We also talk about the camera model parameters, and we distinguish two different kinds of parameters. We have parameters that we call intrinsic parameters, okay, and the way of remember what an intrinsic parameter is, a parameter that if I move the camera, it does not change. Okay, so for example, the focal length, the resolution of the CCD array, those things are intrinsic to the camera. Okay, and extrinsic parameters is basically what it changes when you move the camera, and that typically they are described in terms of rotation and translation with respect to some reference frame. Okay. All right. So I finished class last time by introducing the pinhole camera model. So we talked about a thin lens, and we saw how when we take an image with a thin lens, the image gets inverted with respect to the object. So instead of using that model, what we did is we switched the image plane in front of the center of projection, and that gives us the pinhole camera model. And the advantage of doing that is now that the image of the object is not inverted, okay? It's not upside down. The advantage of that is that we're not going to have to carry negative signs all over the place. Right? If we have the inverted image, we will have negative signs that is just a pain to keep with them, okay? So based on this little diagram, right, we derive the equations of perspective projection. So I started with a 2D picture, right, where here this horizontal line is what we call the optical axis that's perpendicular to the image plane. Here I have the image plane, and that image plane is at a distance f, which is the focal length of our camera, with respect to the center of projection. So I'm placing a camera coordinate system at this a standard position, and we're going to use that standard position all over semester, where the center, the origin is at the center of projection. The optical axis is aligned with the z-axis of the coordinate system, and then of course x and y are going to be perpendicular to that. So x and y are parallel to the image plane. Okay? So here I have a 2D cut where I'm only seeing the x-axis and the z-axis. Okay? And then what we did is we put an object in the world that has coordinates big X and big Z in this coordinate system, in this reference frame. Again, it's the reference frame that's attached to the camera. And then we found the image of this point P by casting a ray from the center of projection and intersecting that with the image plane. And we call that image point little p. Okay? Now, this point will have coordinates in this 2D cut, little x. And for the z coordinate, it has to have coordinates f, because the focal plane is at a distance f from the origin. Okay? So this point has x, f coordinates. And then we just use very simple geometry, similar triangles, to find an expression for little x as a function of big X, big Z, and the focal length. Okay? And this is what we call the perspective projection equation. Okay? Right, so this we did it with a cat xz. Of course, I can do the same thing with a yz, right? So I have a very similar equation. And so together, they make the perspective equations for a camera and the 3D world. Okay, so I have a 2D image plane, right? I'm projecting the 3D world into this 2D image plane using these equations. Okay, right here. Okay, and again, I cannot emphasize it enough. These equations were derived assuming the coordinate system I described, right? The coordinate system is at the origin. The origin is at the center of projection of the camera. The z-axis is aligned with the optical axis that's perpendicular to the image plane, and that image plane is at a distance f from the center of projection. Okay? These equations are true if this is the convention I use. The moment I change the reference frame for this point P, I will have to change these equations, right? I need to transform my coordinates into this reference frame, and then I can use equations. And we're going to talk a lot about that today, or next class, okay? Everybody clear? Again, interrupt me. I tend to speak too fast, okay? All right, so one thing that we noted at the end of the class is, the first thing is that any point in this ray from O to big P will have exactly the same image location, right? Because, again, the algorithm to finding the image of a point is casting that ray and intersecting with the image plane. And so if that point is on that ray, they all are going to intersect at the same place, little p. Okay? So that gives us the first drawback of this equation, which is that we are losing the depth information. Right? Any point on that ray, doesn't matter how far or how close it is, as long as it's on that ray, it will land on the same place. Okay? The other thing is, that I don't think I mentioned last time, is that these equations are nonlinear. Okay? What do I mean by nonlinear? What does it mean that they're nonlinear? What makes them nonlinear? Let's put it that way. The fact that I'm dividing by z. Okay, so if I have 2 points and I add their coordinates and I take the perspective projections, the sum of those perspective projections will not be the projection of the sum. Okay, and we're going to see that later. That means, for example, that the middle point of a line segment does not project to the middle point of the projected segment. Okay, we have foreshortening in perspective projection. All right, so that's another consequence of these very simple, equations. All right, now the fact that it's nonlinear sometimes is a problem. And sometimes, if we can, we try to simplify these equations in a way that become linear. Okay? And one of the times that we can do that is when my objects are far away from the camera. Okay? So if I have here a little cube, okay, which is basically at a distance z0 from the center of projection, where z0 is fairly large, compared to the size of the cube. The size of the cube is delta. Okay? Then what happens is that when I project points on that cube, right, and I put those in the equation that we derived last class, what happens is that basically delta is very small with respect to z0, and so I can drop it out. I can neglect it, right? And so now my projections of all the points around in this cube, they are basically f times x over c0. Okay? But c0 now is a constant. It's the depth of that cube. All right? So now you can think of f over c0 as your new focal length. And basically what you're just doing is scaling x and y. Okay? Now, can you think of situations where this assumption is true? Like a landscape or an aerial picture, right, from very high above in the sky, and you look down, basically everything looks, the height of the object is very small compared to how far the camera is. Okay? So it's a valid approximation in many cases, and it's a useful approximation. Okay. So in this case, we have linear equations. Okay, and basically that's what it's doing is an orthographic projection. Okay, we can also have a model which is a mix between perspective projection and orthographic projection, which is called the Wick perspective model. Okay, and in the Wick perspective model, again, we use these equations. Again, we're assuming that the objects are far away, right? But now what we're doing is scaling things. Okay, by some amount. And what the scaling factor, of course, depends how far my objects are. So still there's a dependency on z, right? But not everybody's at the same depth, but they are all fairly far from the camera. Okay, and that gives me the Wick perspective projection. Okay, so it's basically an orthographic projection. You just copy things, and then you shrink them. Okay, but the shrinking depends on how far things are. All right, so what we're going to do next is actually look even deeper on these very simple equations to try to understand why it's true all of the things I have listed here. Right? When we take a picture of the 3D world, and if there are squares on that world, typically the images will not be squares. And if there are circles, typically the images will not be circles. And I can have parallel lines in the world, but the image will not be parallel lines. Okay? So we know this to be certain. In fact, we discussed last time how this artist had made this picture very realistic by following these rules, the rules that we intuitively know they are true. Okay? Now what we're going to try to do is actually prove that these things are true. Okay? And we're going to try to do using the equations that I just derived. All right? Okay. So these are properties that, again, they can be seen from the equations. First of all, we just discussed they're nonlinear equations. The next thing that we're going to do is we're going to show that if I have a line in the 3D world, unless I have lens distortion, but with a pinhole camera model, the projection of that 3D line is going to be a line. Okay, so if I have something that looks like a box, right, it will be some kind of box, maybe deformed, but it won't become curved. Okay, it will be straight edges. Okay, we're also going to see that it does not preserve angles, and we're going to see that by the fact that, for example, parallel lines will not project as parallel lines. Okay, and we're going to see why or how circles actually get projected into ellipses. Okay, and of course this one we know it already. Farther objects appear smaller, right? Why is that? Why farther objects appear smaller in images? But what in the equation like that? Z. I'm dividing by Z, right? So the bigger Z it is, the smaller the image is going to look like. And again, that's why I can cover the moon with my hand. Okay? All right. So let's look first at projecting lines. So that means that we need to have equations to deal with a line in 3D space. Okay? How do you describe with equations a line in 3D space? As a vector, okay, and just a vector? Well, the vector and the angle, yeah, that will give me the orientation, but I need something more.
Y to the next speed.
Okay, so how do I do this? Okay. All right. So you say something like that? Okay. What kind of line is this? Where does it live? It's a 2D, right? So I have X, I have Y, right? And I have some slope and some intercept. Okay? He was a little closer, actually. So, because this is just 2D, I'm interested. Eventually, I will project my line in 3D to 2D, and we will talk about this equation in a few minutes, okay? But first, I need to have the line of this light up here in the ceiling, okay? How do I represent that line in 3D? What's the equation of a line in 3D?
X minus x1 upon a equal to y minus y1 upon b equal to z minus z1 upon c.
So you have like a couple equals, right? So what that means is that you have more than one equation, right? So we're then in a good track, okay? So one way could be, and that was my next slide, if you are looking at the slides in Blackboard, you can see there, right? Is I can have the line as the intersection of two planes, right? We know that two planes intersect on a line, and we know the equation of a plane in 3D, right? What's the equation of a plane in 3D? How does it look like? Anybody? Yes? Right? So I have something like this. This will describe a plane in 3D. So now I have three axes, right? X, Y, Z, and some plane here, right? Can be described by that equation. And I'm saying, well, my line belongs to that plane, right? I can also have a plane on the line I am interested on, right? And so it means that every point on this line has to satisfy this equation, right? Is that enough? No, right? Because any point on the plane also satisfies that equation. So I only need the points on the line, and that's why I need more than one equation. And that equation will be given by another plane that contains the line, that has equation a prime x plus b prime y plus c prime z plus d prime equals 0. So we have this system of equations, and now every point on the line has to satisfy this, and actually they're the only points that satisfy both equations at the same time. Okay? So that's one way. All right? Unfortunately, for what I'm going to be doing next is not the most helpful type of writing my equations. Okay? So I'm going to go closer to his suggestion. He said I need a vector. Okay? So I have a line in 3D. Right? And he said, let's have a vector, right? That vector is giving me the orientation of the line. But that means that this line has the same vector, and this line has the same vector. So how do I fix which line I want? I need a point. Okay? So let's call that point P. Right? So now I have a line in 3D can be described as a point and a vector. Okay? How would be the equation for doing that? How would I describe any other point on that line? Let's call this vector V. Okay? And I want to find the coordinates of this point R on the line. Okay? How do we express the coordinates of the point R? Using P and V. That's it.
The distance between the two?
Right. So how do I go from here to here? Well, I'm going to add to the coordinates of P this bigger vector, right? And this bigger vector is the vector V that I gave here, scaled by a suitable amount, right? Depends, I mean, if this has length 1, that will be times the distance. But if whatever it is, I need basically to know how much, right? So what I'm going to say is that the coordinates of R can be written as the coordinates of P plus some scaling factor, lambda, times my vector V. Okay? And now I can describe any point on that line, right? What do I need to do to have any point on the line? It's not just for R, right? But for any point. So what? Change lambda, right? So lambda can go from minus infinity to plus infinity, and I cover all the points on the line. All right? Okay? Now, suppose that I didn't even give you a vector, but I gave you 2 points on the line. Right? 2 points defines a line. Is enough. Right? So how would I represent the line if I give you P and Q? I can always define my vector V because I just said V has to be along the line, doesn't matter how big or small it is, right? So I can define V as, for example, Q minus P, right? That will give the vector along the line. All right? Okay. Now, this is a compact single equation, right? Before I had 2 equations. Where is the catch? No. It's really one equation. How many equations is that? 3 equations, right? What it's saying is the x coordinates, the y coordinates, and the z coordinates of the points need to satisfy that equation. Okay? What it's saying is that x sub r has to be equal to x sub p plus lambda b sub x, the first component of v. Y sub r is y sub p plus lambda by, and z sub r is c sub p plus lambda bc. Okay? So I really have 3 equations. Okay? Questions? No? Okay. Now, how do I prove that the image of a line in 3D is a line in the image plane? How would you go about proving that? You know it's true, you see it with your eyes all the time. But how do we prove that our model explains that? What would you do?
You can plug it into the plane equation.
I can do that into, take these points, these equations, right, and combine them with my model. Right? My model was the perspective equations, right? So it says that little x is fx over z, y is f y over z, and of course little c is f. Right? These are the coordinates of the image of a point in 3D. Right? So I could plug in these three equations in here, right? And then I will have to show what?
Similar line like this, equations remain linear.
Right. So for example, I could project P, I could project Q, I could project R by using these equations, right? And then I will have to check whether little p, little q, little r are indeed aligned. And you can do that after a couple of pages. Okay? So I'm going to do it in a much more simple way. Okay? We're going to go back to geometry. Okay? So how can I use geometry to prove that the image of a 3D line is aligned in 2D? How do I do that? So I have my coordinate system. I have my image plane perpendicular to that optical. Let's draw it a little bigger. Right, it's perpendicular to that image plane. Here's my center of projection. This distance is f. And I have a line in 3D, and I'm going to project that, right? So what we said is if I have 3 points, P, Q, and R, I could project them, right? I will get P, I will get Q, and I get R. And what I'm saying is I shouldn't be getting something like that. What I should be getting is something where Q should be there. Right? The image of a line should be a line. How do I do that geometrically rather than writing a lot of algebra? Look at the figure. Yes?
The intersection of P, Q, and R plane form a straight line.
Close, yes. So the center of projection O and my 3D line define a plane. Yes? A point and a line in space defines a plane, a unique plane. Okay? The rays OP, OQ, and OR, they are on that plane. Why? Because O is on the plane, and the points on the line are on the plane, so that line has to be on the plane. Okay? Now, little p, little q, little r are on these rays, so they had to be on that plane. Do they have to be in a different plane also? Which plane? The image plane. Okay? So they have to be in two planes at the same time. It means they have to be in the intersection of the two planes. So it is a line. Just 3 lines of English. Okay? Again, you can try at home to do the math for deriving the points. It's doable, but it's messy. Okay? All right? Now, can you extend this proof to show that the images of a circle is in general an ellipse? Yes?
I guess if you had a circle, it would form like a cone.
Exactly. Right. So now I have a circle in 3D world, right? The circle and the origin, the center of projection, define a cone. The rays are on the surface of the cone. So the image of those points on the circle will be on the surface of the cone. They have to be also on the image plane. So it has to be intersection of both. And in general, the plane will intersect my cone in a circle, an ellipse, sorry. Okay. Now, sometimes we'll intersect it as a circle, right? When would that be? When the image plane is parallel to the disk, right? In that case, the image will be a circle. Okay? But otherwise, it will get deformed into an ellipse. All right? Okay, so now let me introduce a concept that you might have seen before if you did any projective geometry. Which is the concept of, hopefully this, ideal point. Okay. Can you check if this is going on?
Yeah, it's okay.
Thank you. Yeah, last time we have a problem when I took off my sweater, we lost audio for a few minutes. So, if I have a line, right, I have an infinite number of points. We saw the equation of the line involved that lambda, and I can vary lambda from minus infinity to plus infinity to slide my points all over the line. Okay? As lambda goes to infinity, I keep going and going, right? I go forever. That point at infinity, we call that an ideal point or an improper point. Either name basically means the same thing, synonymous. Okay? And it's something that we're going to be playing a lot in this class because the orientation of the lines have a lot of information in general for things that we want to do. And what we're going to see is that the image of this point at infinity not always ends up being at infinity. Sometimes actually becomes a very finite point, a point that I can pinpoint on the image plane. Okay? And the image of that point at infinity, we call it the vanishing point. Okay? So I have a point in infinity, and when I project it, it becomes a finite point. Okay? That point is called the vanishing point. All right? And it carries information about the orientation of the line where it came from. We're going to see that in a minute. Okay? Okay, so we have done this, although I advise not to do this to prove that things were in an image, right? But we could do that, right? We could combine the equations of a line in 3D using the vector format, not the intersection of two planes, and plugging in this into the perspective projection equations to get the coordinates in the image plane of the projection of any point on that 3D line. Okay? And of course, the last one is F. Okay? So we did that. Okay? Did that. That's the geometry. Okay? Now let's talk about the image of the ideal point. Okay? How do I find the image of the ideal point? What do I need to do? We say the ideal point is the point at infinity, right? So that means that lambda is equal to infinity. So what I'm going to do is take the limit in these equations when lambda goes to infinity. Okay? Now, let's assume for now that CP is different from CQ. What does that mean geometrically? That CP is not the same as CQ. What will happen if CP was equal to CQ? What can you say about that line? It's parallel to the image plane. Okay? So for now, I'm going to assume that that line is not parallel to the image plane. It means it intersects the image plane. Okay? It might be out of the field of view of the camera. Doesn't matter. But if I extend my image plane all the way to infinity, that line intersects somewhere. Okay? All right. So now, assuming that, okay, let's see what happens when I take lambda all the way to infinity. Okay? What happens in the first equation? This guy, xp, is very small compared to lambda times something, right? So it goes away. This cp, same thing, is much smaller than the second term, so it goes away, right? So what I'm left is with f, okay, times this factor over this factor, and what happens to lambda? Cancels away, right? So the x-coordinate in the limit, when lambda goes to infinity, has a finite value. Okay? And that value is equal to what? F times x cubed minus xp divided by c cubed minus cp. And of course, I can do the same thing with the y-coordinate, right? And with the z-coordinate, well, still f, right? All right, so I get these limits. Now, look at this expression over here. Does it depend on the point P or the point Q? If I change the point P that I'm using as reference, and I keep the same Q, for example, does this limit change? It's a tricky question. No, why not? But how? Why? It depends on the difference between them, but not on each of them in particular. And really, so what it means is it depends on the vector q minus p. It depends on the orientation. Because if I change xq, I have to change zq in a way that the point q is still on the line. Okay? So what we're saying is I am keeping, right, the vector v, the orientation of the vector v. I can change the magnitude, but the orientation of the vector v does not change. Right? So these equations over here do not depend on the particular point P or Q I picked. They depend only on the difference between them, which gives me the orientation. And the magnitude doesn't matter because the magnitude will cancel out in the numerator with the denominator. So it doesn't matter how far apart they are, as long as both of them are on the line. Okay? So what is the consequence of this? What happens if I have a bunch of parallel lines? What happened to the image of their ideal points? What can you say about them?
instead of being parallel, they intersect at the point?
Yeah, where?
At the limit?
Yeah, at this, right? Because again, it doesn't depend on the point P, it depends only in the direction V. So if I have, hope you can see here in the bottom. If I have two lines that are parallel, this has his own P1, this has his P2, but these two share the same vector V, right? So the image of the ideal point of this line and the image of the ideal point of this line is the same, because only depends on V. Okay? So all parallel lines seems to be concentrating at the vanishing point. Okay? And that's what you saw in that painting I show you, where you have a checkered floor, and all the lines of the floor seem to be going into a point. Okay? Which is not really, the lines, the floor ended before reaching that point. But if you prolong those lines, you will see that they meet at that point. Okay? And that's how you actually paint accurate perspective projection deformations. Right? You pick your vanishing point, and then you cast rays that are coming out of those. And those are all parallel lines, are images of parallel lines. Okay? All right. What happens if CP is equal to CQ? So we say the line is now parallel to the image plane, right? So what happens when I take the limit?
The limit doesn't exist?
Well, the fine doesn't exist. I mean, it's not finite, but, right? So what happens when CP is equal to CQ? What happened to the denominator? No, not to 0. It goes to CP, right? This term, this term is 0, but this term is still there, right? This term is 0, so the term is there, right? So now I take the limit of this, so this term is not there, and lambda goes to infinity, and so the limit is infinity, okay? So if by that you mean it doesn't exist, well, yeah, it goes to infinity. It's not finite. Okay? So what that says to us? That if I have lines that are parallel to the image plane and they're parallel to each other, would they converge on the image? No, they will be parallel. Okay? So that's the case when parallel lines get image as parallel lines, if they happen to be parallel to the image plane. The same way that a circle became still a circle if it was on a plane that was parallel to the image plane. Parallel lines will project to parallel lines if they're in a plane that's parallel to the image plane. Yes?
So ZQ equals ZP, does that mean it's just a point?
No. It means that they have, let me show you. See this plane over here, which is the image plane? Any point in this plane has a third coordinate equal to the distance from the plane to the center of projection, which is Z. If I have a line that's parallel to that, I can put a plane that's parallel to the image plane. All of these points in this line have depth Z. Okay? So they have different X and different Y's, but the Z is the same. You have a question? Okay. Okay, we did already the circle, so we're here. Okay. So again, if you took all these lines they're all parallel to each other because they're all on the ground floor and they're parallel, they're the tiles, they will converge to a point, right? If you're in a very straight road, like the highway, and you look far ahead, or you are in the train and you look at the railroads, the line seems to be meeting at that point. Where? At the horizon. Okay? So the horizon is actually the projection of all these points at infinity. Okay? So it's the image of a line that is made out of these all ideal points in space. Okay? And one nice thing is that we're going to see is that in perspective projections, on projective geometry, points at infinity are not any different than points that are finite. We treat them all equal. Okay? And for that, we're going to introduce a little bit of notation. Okay? But you're going to see that the advantages are that now we can handle any type of line the same way. Okay? Yes?
So different parallel lines will converge to different points, right?
Right.
But do they all fall? Do all the points end up falling on the line?
Yes. Yes. We can show that. Okay. All right. Okay. So we are used most of the time, that's the geometry that we'll deal with, was called Euclidean geometry. Okay? So in Euclidean geometry, if we are working in 2D, right, like the first line that we talk about the equation, we describe points using 2 coordinates. Right? So we typically pick 2 axes that usually are orthogonal. They don't have to be. They have to be linearly independent, but usually we pick them orthogonal. And then points are described with these 2 coordinates, x and y. Right? And if we are in 3D, we have 3 coordinates, x, y, and z. Okay? So today what we're going to do is introduce one more coordinate. So if we're dealing with 2D, we're actually going to use 3 coordinates. And if we are dealing in 3D, we're actually going to use 4 coordinates. Okay? It seems messy and extra and a waste, but actually it's very useful. Okay? So bear with me. Okay? All right. So again, point is described with x, y. Now what we're going to do by introducing this 3rd coordinate, okay? And let's, for 1 second really only, because in the next slide I'm going to change that, let's assume that that 3rd coordinate is equal to 1. Okay, so again, seems wasteful because if I know it's 1, I don't even need to write it down. I just drop it. Okay? Now, what we're going to do is actually make a class of equivalence where we take these 3 coordinates and multiply by, for now, a non-zero constant, k, and we're going to say that they represent the same point. Okay? So if I have kx, ky, k, remember the last one was 1, right? That represents the same 2D point. How do I go from these coordinates, funky coordinates, to my traditional Euclidean coordinates, the 2D coordinates? What do I need to do? Just divide by the 3rd coordinate, right? So if I'm going to do division, I hope k is non-zero, right? So I take the 3rd number, divide the first 2, and I get back my xy. So you see that I can go back and forth between this, right? No problem with that. Okay, so again, xy1 and 2x, 2y2 is the same point. 3x, 3y3 is the same point. I just divide by k and I go back. Okay? Now, this trick is going to be useful in many ways. Okay? How many of you have done computer graphics? Nobody. Okay. When you need to apply a geometric transformation to points, we're going to see in a few slides that you can do that by taking the point and applying a matrix to it. Okay. Now, we would like to do that for rotation, and you might remember that the rotation is represented with a matrix. But we also want to do it with translation. Okay. And this last coordinate is going to help us doing that trick. Okay, so that's one reason. But the other reason, which is actually more fundamental and I think neat, is that if I allow k equal 0, I can now represent points at infinity. Okay? So we're going to keep k equals 0 to represent the ideal points. Okay? So now with these three coordinates, I can represent finite points and ideal points. The ideal points have k equals 0. Okay? And then I can apply my equations nicely, okay, and treat all points the same. I am colorblind in terms of whether it's a point at infinity or it's a finite point. Okay? In fact, now I can say that in projective geometry, all parallel lines always intersect at a point. They intersect at the ideal point. And if they are not parallel, they also intersect that point. So any pair of lines, doesn't matter whether they're parallel or not, they intersect a point. The ones that intersect at an ideal point is that we call normally parallel lines. But we're going to see that equations doesn't really make a distinction between them. Okay? Now, P2, we're going to use it to call about this plane when we're using three coordinates. Okay, so we are working on a plane, for example, the image plane. Normally in Euclidean coordinates we have two coordinates, but we're going to go to projective coordinates and then we have three. Okay, and we call that P2. In space, we go from 3 coordinates to 4 coordinates. Okay, and we call that P3. Not surprising. All right. And again, it's the same idea. I have an equivalence when I take the 4 numbers and I multiply by a constant k. And when k is 0, that's a point at infinity. Okay. All right. So let's work with the line in 2D. Okay. Now, I'm not going to use the equation that he gave me. He had a slope-intercept equation, but you agree that this equation, it also represents a line. What's the advantage of this equation versus the slope-intercept?
XY intercepts here.
So it doesn't matter the orientation, right? So if my line is parallel to the y-axis, I cannot use his equation because now that equation becomes x equal constant. So his assumption was the coefficient of y, I could always make it 1. Okay? This one doesn't matter the orientation. It represents all lines in 2D. Okay? I just need to change A, B, and C. All right? Now, what happens if I take that equation and I multiply it by k?
Line remains the same.
It's the same equation, right? It's the same line. All the points do not change. They just change the representation, but that's all. It's an arbitrary scaling of the equation, but still, I get it. So what I'm going to say is that A, B, and C, and Ka, Kb, Kc, again, is the equivalence. Right? So I'm going to represent this line by these 3 numbers, A, B, and C. And I can scale them as much as I want, okay, as long as I don't use k equals 0, of course. And it's the same line. I don't change things. Okay? All right. So this is the Euclidean representation of the line. Okay. Now, what we're going to write this equation is slightly different. Okay. What this notation means, it means I take a vector that has components A, B, and C, right? I transpose it, okay? And then I do the dot product of that with the vector x, y, 1, and that has to be 0, right? So what this says is that A times x plus B times y plus C times 1 has to be equal to 0. Just as it's a different way of writing down the same equation, right? So I have now a dot product between 2 vectors. Each of the vectors has 3 components. Okay? Now, if I multiply by k, same thing, right? And I can put the k either in the ABC or in the xy1. Doesn't matter, right? But what this is saying is that this representation works well with my projective coordinates, right? Because it's saying I scale the coordinates by k and the equation is still valid. No change. Okay? So the projective representation of a line is given by the dot product, and one vector represents the coefficients of the line, a triple, A, B, C, and the second vector represents the coordinates of a point on that line. Right? And you see that I can scale either U or P or both, and still it's the same equation. Okay? Again, as long as my scaling factor is not 0. Questions? Okay. All right. Now, the other neat thing is that you can look at this equation in two different ways. Okay? This is a dot product, right? A dot product is a scalar, correct? And the transpose of a scalar is the same, doesn't change, right? So I can take this and transpose it. How do I transpose a dot product or a product of vectors in algebra? What I need to do is transpose the matrices or vectors and reverse the order of multiplication. Okay? So this and this is the same. Right? And so now I can look at this equation as saying two different things. I can say I have P is a point lying on the line U. So U is your parameters, right? And now I find P lying on U. Or I can say I have a line P going through a point U. I can reverse the role of these things because both of them have 3 numbers. So who am I to say that the 3 numbers are the coefficients of the line or the coordinates of the point? I can, either way, that would be a valid assumption. Okay? And any idea why that might be neat and not confusing? Why those 2 interpretations might be useful? Nobody? It means I get a lot of theorems for free. Why? Any guesses?
You can find all the points that pass through, all the lines that pass through a point, or the points that lie on the line.
If I prove a geometric proof of a theorem or something that involves points and lines, I can swap the roles. Wherever I was saying the word line, I can say point. And wherever I was saying point, I can say line. And I get a new theorem that's also true. Okay, that's called duality. Okay, so I can prove things in one setup, and I get for free the mirror of that by just reversing the role of points and lines. Okay. All right, so let's look at an example of that. We know that 2 lines always intersect on a point. Always. Why? Because I introduce my ideal points. Okay? So even if they're parallel, they will intersect at their ideal point. Okay? So here I have the equation of one line, and here I have the equation of another line. And I'm saying I'm using the same x, meaning I'm looking for the point that belongs to both lines, the intersection point. Okay? So first line has a representation of the vector L that has 3 numbers. Second line has a vector that has also 3 numbers, but I call that L prime. So these 2 vectors are different. Okay? But I'm saying they have a point in common, x. So that x has to satisfy this equation and this equation. Okay? So what does it mean that I have a dot product equal to 0 between 2 vectors? What's the geometric interpretation of that? Forget that I said that it represents a line. So if I give you 2 vectors, now in Euclidean space, and I say their dot product is equal to 0. They're orthogonal, yes. They're orthogonal to each other. Okay? So this means that the vector x and the vector L are orthogonal. Okay? And this says that the vector x is also orthogonal to L prime. So I have a vector that's orthogonal to another 2. How do I get a vector in that direction? If I know this vector, I know this vector, and I know the vector I'm looking for has to be orthogonal to the 2 of them. What's the operation I would do? Cross product, right. Okay? So x is given by the cross product of the 2 vectors, L and L prime. Okay? So I give you 2 lines. I want to find intersection of the line. Very easy. I just do the cross product of the 2 vectors. I think that's cool. I'm geeked that way. Okay. Anyway, I talk about duality, right? So here I have 2 lines passing through a point. What would be the dual of this? Remember, you need to change point by line and line by point, and you're okay. So here I have 2 lines intersecting on a point. What is the dual of that? 2 points define a line. Okay? So I give you 2 points, and I want to find the equation of the line that passes through that point. How would I do that? Based on this, what do I need to do? No. Yes?
Would you take the cross product of the points?
The cross product of the points. Again, replace points by lines, lines by points. Okay? So where here I have a point, I put a line. Where here I have the lines, I put the points. Okay? So point cross point will give me the parameters of the line that is joined by the 2 points. Okay? Now, remember, I said for us, parallel lines are just any 2 lines. I don't really they have any special treatment for them, thanks to this 3rd coordinate. Okay? So let's look at this example where I have 2 parallel lines. Okay? Here I put them parallel to the y-axis, but in general, if I have 2 lines that are parallel, it will be represented up to a constant, of course, but the first 2 numbers will be the same. Why? Why the first 2 numbers will be the same? Or up to a constant? Because they're parallel. But what does it mean that the 2 numbers is what? The slope, right? The slope is defined by the ratio of these 2 numbers. Okay? So if they're parallel, the first 2 numbers are the same. And what would change the 3rd number, right? If all numbers were the same, then it's the same line, right? But if I had 2 different lines, the first 2 numbers will be the same or a scale version of each other, and the 3rd number will be different. Okay? Now, I said that the intersection of 2 lines is given by the cross product of the vectors representing each of the lines. So here I have ABC, ABC prime. I do the cross product of that, and you can do that in your free time, but believe me, that's the answer, right? And what you see is that the 3rd component is 0. Okay? And what does it mean that the 3rd component is 0? It's an ideal point. Lies at infinity. Okay? Now, how about the first 2 components? I didn't use this. I used just B, and I used minus A. Why did I do that? I just simplify by C prime minus C, right? Which I'm assuming is not 0, because it's not the same line. Right? And any scale version of that is the same, so I just drop the C prime minus C. So the point, the ideal point, has coordinates B minus A. Okay? Now let's look at this example over here, right? 2 parallel lines to the y-axis. So the first line has representation 1, 0, minus 1. Do you agree with me? Okay? Because the equation of this guy is x minus 1 equals 0. Right? So the coefficient for x is 1, the coefficient for y is 0, and the coefficient for z is minus 1. Okay? And for this line, I have 1, 0, minus 2. Now, let's do the cross product of the two. And I get 0, minus 1, 0. Or again, I can scale. I can change the sign. That's OK. And I get 0, 1, 0, which is the vertical direction, which is the orientation of the line. Okay? So the ideal point, okay, is along the direction of the line. Okay? Questions? Okay. And again, as I said earlier, anytime that you have a theorem that involves points and lines, you reverse the role of them and you get a theorem for free. Okay, so I can do this representation or this representation. I can do the cross products to get the intersection of two lines or to get a line between 2 points. And we're going to see later on more of examples of this. Okay, so to summarize, this is our model of the projective plane. Okay, and what we know now is that the image of a line is always a line. That given 2 points, there's always one line that joins them. And given 2 lines, there's always an intersection between the two. Doesn't matter whether they're parallel or not. Okay. All right. So now let's talk about geometric transformations. And again, here is we're going to see the advantage of introducing that third coordinate. Okay. So what we're going to see, and I'm going to show this picture several times today and in the rest of the semester. Okay. Where we have is a hierarchy of geometric transformations. Okay, so I'm going from the left to the right, from more specific or particular to more general transformations. What that means is that a transformation of the right includes, as a special case, a transformation to its left. Okay, so here's the order of my transformations. So I have translation. So I take this square and I move it. Okay. I can also not only translate it, but I can also rotate it. Okay. So a combination of rotation and translation, we call that an Euclidean transformation. Okay. So it doesn't distort the object; it just moves it and reorients it. Okay. Then we have similarity, where we scale things. So now the square not only moves and rotates, but also shrinks or expands. And then I have affine transformation, okay, where now the square has become a parallelogram. Okay, so parallel lines remains parallel, right? But the angles are now preserved. Right? Because I had a 90-degree angle here, and now I don't. Okay? So parallelism is preserved, but angles are not. Okay? And then finally, the most generic transformation on the 2D plane is what we call the projective transformation. So it takes that square and transforms it into still a quadrilateral, right? But it's not longer parallel lines are parallel anymore. Okay, so I get a kind of a trapezoid there, right? Some quadrilateral is a closed form, but not necessarily I have parallel lines anymore. Okay, so what we're going to do is derive equations for all of these transformations. Okay, why I might need this in this class? Why are we doing this? Any guesses?
When we look at a photograph, it's a transformation of any geometric shape.
Right, and also remember those very nice simple equations that we derive where I have the perspective projection, and I try to make you pay attention to the fact that those equations were only valid for that reference frame. Okay, so what will going to happen is that my objects in general will be expressed not in that reference frame, but in some other reference frame. And so I will have to change the coordinates, okay, to go back to the camera coordinate. And for that, I'm going to be using this portion of it. I'm going to be using translation and rotation, okay? And then I'm going to do the projection, the perspective projection. And I'm going to be around here, okay? And depending whether I can assume that my camera is far away, I might be able to just assume a fine, okay? But that's the idea why we're going to be doing this. All right. Okay, so let's start with the easiest one, translation, okay? So here I have, it's all on the plane. Right now we're all doing 2D. Later on we're going to move to 3D, okay? And I'm going to have this square, which right now is at the origin of the coordinate system, and it has size 1. And I'm going to translate it, okay? And I'm going to translate an amount tx in the x direction and ty in the y direction. Okay? So that means that a point that had coordinates x and y here, after the translation, will have coordinates x plus tx and y plus ty. Yes? Right? So I just need to add that translation vector to my coordinates, and I get a new coordinates. Okay? For example, this guy had coordinates 0, 0, and now has coordinates tx, ty. Okay? Now, I want to write these equations in a matrix format. Okay? What I want to be more specific is I give you the old coordinates x and y, the coordinates before the translation, and I want you to do a matrix product and give me the coordinates x prime, y prime. How do I go from this addition to a product? How do I write this as a product of matrices and vectors?
Multiplied by 1 tx, 1 ty. So, x prime and y prime equal to matrix 1 tx, 1 ty, and then xy.
So I'm going to go back to my 3 coordinates. Okay? I told you, right, that we were going to see that this was useful. Okay? So now instead of x and y, I have my 3rd coordinate, and again here I'm going to go to my coordinate equal to 1 for now. Okay? And if I start with a point that has 3 coordinates, I want to end with a point that has 3 coordinates. I don't want to be switching between 2 coordinates and 3 coordinates back and forth, right? So why? Because I'm going to concatenate operations. Okay, so I want to be able to do more of this type of transformation. Say I want to translate one more time, right? So when I'm going to do this multiply again for a matrix, and then I don't want to be changing my dimensions back and forth. So xy is represented now as xy1, right? And the translation matrix is this matrix that has the identity over here, right? 1, 0, 0, 1. And then this last vector here, this column, is again the 3 coordinates of the translation vector, tx, ty, and an extra 1. Okay? And the last row is very boring, just 0, 0, 1. Okay? And you should confirm, right, that when I take this matrix times this vector, I get back these 2 equations once I discard the 3rd equation, which the 3rd equation is a very boring equation. What does it say? That 1 is equal to 1. Okay? But it helps to keep everything in 3 coordinates. Okay? All right. So now I have a point in the plane. I express it with this coordinate. Sometimes we call these coordinates homogeneous coordinates, adding that extra 1. Okay? Multiply by this, which we call the translation matrix, and I get a new homogeneous coordinates. And if I want to go back to Euclidean, very easy. I just drop the last number. Okay? Okay? Now, say I want to do scaling. I also can write the matrix equation for that very easily. What I need to do is just, I put in the diagonal not the identity, but the scaling factor. Right? So that scales the x coordinate by this amount and the y by this amount. And here I have both scaling factors the same, but I could change. I could scale more on the x direction and less on the y direction, for example. Okay? Now, rotation. We're going to rotate around an axis that's perpendicular to the plane where that square lives. Okay? So the convention that we're using is that we are rotating around the z-axis coming out of the screen. Okay? And when we rotate clockwise, the equations for the rotation are given by this. Okay? And again, this is probably the rotation matrix that you have seen before. What we're doing now is adding this extra column and row that allows us to work with the 3 coordinates. Okay? Why do I do this? Again, because I would like to mix rotations and translations, right? And so I want all my matrices to have the same dimensions. So I can concatenate one operation after the other. Okay. So, for example, if I want to do rotation and translation, the matrix becomes like this. And again, this portion over here is the rotation portion. And this last column over here is the translation portion. Okay? Now, what it matters is the order in which I make the operations. Right? If I translate first and rotate afterwards, I get this. If I first rotate and then translate, I will get a different matrix. It's not the same. Okay? And the short answer why that's the case is because multiplication of matrices is not commutative. Right? So think about applying first the translation matrix and then the rotation matrix, you get one result. But if you flip the order, you will get a different result in general. Okay? So order does matter. Okay? Okay, so it's going to be convenient to partition our matrices and notice the different portions of it. So again, clearly here, this portion is the rotation portion. This portion over here is the translation portion. And this over here is that last row that I need to do so my operations behave nicely when I do products. Okay? Okay, so for example, I will write this as like something like that. R means rotation, T means translation, right? The rotation matrix is 2 by 2, and it's a rotation matrix. So what's the determinant of a rotation matrix? If I give you a rotation matrix and I ask you to compute the determinant, do I have to be more specific? I have to say rotate by 35 degrees around the z-axis, or can I say just give me the determinant of a rotation matrix? Doesn't matter the angle. It's 1. Doesn't matter what theta is. Okay, the determinant of rotation is 1. That also has to do with the fact that when you rotate things, things do not change size. Okay. The other thing is that actually the vectors are orthogonal to each other. Okay, so the rows and the columns are orthogonal to each other. And it's very easy to invert a rotation matrix. What's the inverse of a rotation matrix? The transpose. Okay, so you can invert the matrix. And again, think geometrically. When you do a rotation, you multiply by a matrix. Okay, if you want to go back to the original location, that would be the inverse operation, right? And that would be rotating by minus theta. Plug in minus theta in this equation, and you will see that basically you get a transpose equation. Okay? So the rotation matrix is orthogonal matrix. Its inverse is transpose. Okay, and again, rotating an angle theta and going back to the original position, I just need to rotate by the minus theta, or you apply the transpose of the matrix. Okay? Questions? Okay. Okay. Another way of writing the same thing that we're going to use is this. Okay. What this says is I take the 2D coordinates. Now I'm not using the third coordinate. time of the point, apply a rotation to it, add the translation, and gives me the new point. Okay? So this portion over here. So this is matrix form, this is equation form. They both represent the same thing. Okay. So again, I can combine all of these transformations. That's the beauty of using this notation. I can just do this as a concatenation of multiplications of matrices. So for example, I can do translation, rotation, and scaling, okay, again by doing a product of matrices. And again, remember, products is not commutative, so the order does matter. And you write the matrices in the order from right to left. The first matrix that you apply is the rightmost. That goes applied directly to the point. To that result, you apply a new matrix, so you write that to the left of that. And to that result, you apply another matrix to the left of that. So it's from right to left, the same way that you write Hebrew and Arabic, that. All right? Okay. So here is the affine transformation. Okay, remember affine transformation is the one that preserves parallelism. So these two lines are parallel to each other. After the transformation are parallel to each other. These are parallel, they are also parallel. However, the angle is not preserved. Okay, so the 90 degrees is no longer 90 degrees. It becomes a parallelogram. And the generic equations for an affine transformation can be written like this, okay, which is very similar to the similarity equations I gave you before. What's the difference here? I say that this is more general than the Euclidean and the similarity transformations. What's different from the previous equation I had? No, this is still 3 by 3, right? So this is 2 by 2. This is 2 by 1. So I'm writing them in a block format, and then I have the 1 equal 1 last row. Yes.
Is it because there's like an intercept now? Like before, it was just a scaling, and now you're adding like a vector.
Yeah. So the main thing is this A. Okay, when I had Euclidean, which is just rotation and translation, what was this matrix here? What kind of matrix is that? It's a rotation matrix, right? And I said the rotation matrix is not just any matrix, right? It's a very special, nice matrix that has a determinant equal 1, okay? The inverse is transposed. The rows and the columns are orthogonal to each other, okay? So not any matrix is a rotation matrix, okay? Here, A can be any matrix, okay? So that's what I'm saying, that as I'm moving towards the end of the axis in my picture of hierarchy, I'm getting more general transformations because this one has a special case, the Euclidean, when A is a rotation matrix. But if A is just any arbitrary matrix, then I end up with this type of transformation. Okay? Now, the most general of all is the projective transformation. Okay? And the projective transformation, the only thing is really is a linear transformation. And in this class, we're going to be dealing with two types of projective transformations. One is that it keeps the dimension that I'm working on. So I might be dealing in 2D and I keep in 2D, or I might be dealing in 3D and I keep in 3D. Okay, so P2 to P2 or P3 to P3. Or I can go lower. I can go from P3 to P2. That is from the 3D world to the image plane. Or I can go actually from 2D to 1D. So I can go from P2 to P1. Okay? So those are the two kinds of projectivities that we're going to deal with. Okay? And here are examples of possible projected transformations, and also one counter example. Okay? So this one here is really the one that we're going to be using a lot in this class, right? We have points in the 3D world, doesn't matter where they are. And we project them through a center of projection and intersect those rays with the image plane. Okay? That's what we call the perspective projection. Okay? That's a projectivity. Okay? That's what we call actually perspective projection. Okay? Over here, I have a special case that says that these points in the 3D world, they actually happen to be on a plane. So now I have points on a plane projected into a plane. There's also projectivity. So this one goes from P3 to P2. This goes from P2 to P2. They're different P2s, but they go from the same dimension to the same dimension. Okay? This one over here is also a projectivity. Okay? And what this is think about I'm now rotating my camera. Okay? But I'm rotating in a way that the center of projection remains the same. So I'm rotating around the center of projection. So the image plane changes, but the center of projection does not. Okay? In that case, this is also a projectivity. Okay? This one, we're going to use it for stereo, for example. Right now I have two cameras, two centers of projections, two image planes, and my scene is planar. That's also projectivity. Okay? Now this one over here, it's a projectivity from these points to these points, and a projectivity from these points to these points. But there is no projectivity between these points and these points. Okay? So that's an example where I do have two projectivities, but I cannot link them together through a projectivity. Okay? Okay, so here is a theorem. I say that a projective transformation from Pn to Pn. Okay, so I'm going from 2D to 2D, or from 3D to 3D. And I want to express that using a matrix. Okay, I'm going to show that a matrix can be expressed. I can find what the matrix is if you give me n plus 2 points. Okay, so if it's from P2 to P2, I will need 4 corresponding points. Okay, what that means is that 4 points before the transformation and the corresponding 4 points after the transformation. If I'm going from P3 to P3, I'm going to need 5 points. Okay, but if you give me those 5 points, I can find the matrix transformation between them. Okay? And the proof is very simple. It's just algebra. You know, it's messy, but not hard at all. Okay? And we're going to do it for P2, but doing it for P3 is very similar. Okay? So what I'm saying here is I have points related by a matrix transformation. Okay, and I'm saying these points belongs to the same dimension. In this case, I'm doing with P2. So that means that P is going to be written using 3 numbers, and P prime is going to be written with 3 numbers. Okay, and I'm going to link those points by this matrix T. Okay, so if P is 3 by 1 and P prime is 3 by 1, how big is T? 3 by 3. Okay. Now, if it was a point in 3D, right? Now I have 4 coordinates and 4 coordinates. That makes it would be 4 by 4. Okay. Now, because it's 3 by 3, I need to find 9 numbers. Right? Now, actually, I don't have 9 degrees of freedom. Why? Nobody? Because I'm working with 3 coordinates to represent points in 2D, I can scale the coordinates of P and P prime by a constant. And so I can scale the matrix T by a constant, and I still will be representing the same thing. Right? And so I don't have 9 degrees of freedom. Really, there are 8. Okay? Because I can scale the matrix by a constant, and it will still represent exactly the same transformation. Okay? Okay, and so the theorem, what it says is to find these 9 numbers is enough to find 4 correspondences. Does that make sense after what I just said? The 8 degrees of freedom and the 4 correspondences. Are those 2 things related in any way? So each point has 2 numbers, right? And each correspondence now, it gives me a relationship between 2 numbers, right? And I need 8 degrees of freedom, so I'm going to need basically 4 equations, okay, to link those 2 numbers. So 4 times 2 will give me 8, which is the degrees of freedom that I have. Okay, it's going to be clear as soon as we do the proof. Okay, okay. So here's the proof. Okay. Without lack of generality, what I'm going to do is for P1, P2, P3, and P4, I'm going to choose this standard basis in P2. Okay? What is the standard basis? The standard basis is the one that has the unit vectors, right? 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay? So a 1 on the x, a 1 on the y, a y on the z. And a vector that has all 1s. Okay? That's my standard basis. So you give me 4 points, and I decide, okay, my reference frame is going to be like that. To the first point, I give the coordinates 1, 0, 0. To the second point, I give the coordinates 0, 1, 0, and so forth. Okay? So this is saying these 2 points are ideal points because the third coordinate is 0. Right? It's the direction on the x and the direction on the y, but really doesn't really matter. Okay? This one is the point that has is the origin, right? Because it's 0, 0 divided by 1 is still 0, 0. So I have the origin, the direction of the x-axis, the direction of the y-axis, and then I have this point. What point is that? The point 1, 1, right? And you can think of the first 2 give me the orientations of the axis, and the last guy, the first 3, sorry, gives me the orientation of the axis and the axis location, and this guy gives me the scaling. Okay? All right? Now, I could play that trick on one side of the equation, but I cannot play the trick on the other side. Okay? So for the other side, I'm saying, okay, the coordinates of the corresponding point will be x prime 1, y prime 1, z prime 1, because it's the image of x1, y1, z1. And I put a lambda over here because really I can multiply by any number and it's still the same point. Okay? And I do the same thing for the second, the third, and the fourth, and each of them has their own scalar multiplying them. Okay? I don't know that. Okay? But what I know is that this point and this point and this point and that point are related by the same T matrix, a 3 by 3 matrix. Okay? Which means is that when I plug these coordinates into the equation, they has to satisfy. And now what I need to do is basically solve for those numbers. Okay? So what I'm saying is P prime is equal to T inverse P, or P is equal to T times P prime. Okay? All right. So let's take my transformation T, multiply it by the coordinates of the first point, the point that has 1, 0, 0. That has to give me the coordinates of this image, okay, which I said were lambda x prime 1, lambda y prime 1, lambda c prime 1. Okay. Now, when I multiply this matrix by this vector, what happens is that I pick the first column of this, right? Because when I multiply this guy by 0, it goes away, and this guy by 0 goes away. So the first one will be T11, and then for the second one will be T21 and T21. Okay? So now you see why I picked this point, right? Because it's very easy now to write this vector, right? That's saying is that the first column of the T matrix that I want to find is given by this vector I have here. Okay? And I can do the same thing for P2 and P3, the second point and the third point, right? So what will happen with the second point? The second point will pick the second column, and the third point will pick the third column. Okay? So what that says is that the matrix T should be like this. Okay? Why do I need the fourth point? The lambda, mu, and nu are bothering me, right? I don't know what those numbers are. Right? I said I have one scaling factor, but now I have 3, right? So that's not what I promised, okay? So I need the fourth point, and so what I need to do is plug in the fourth point, okay? So the 1, 1, 1, 1, and that gives me basically the equations that I needed to do everything up to a scaling factor, okay? So what I get, 3 equations, right, where x prime 1, x prime 2, x prime 3 are known because those are the coordinates of the corresponding point, okay? What I don't know is lambda, mu, nu, and rho, okay? So you can think of this as a linear system of equations, 3 equations, 3 unknowns, lambda, mu, and nu, where the independent term over here really can change it by a factor rho. That's what I'm saying. You know, I have one extra scaling factor that I would never be able to pinpoint, but doesn't really matter because it doesn't matter what that number is. It represents the same transformation. Okay. So maybe that's actually a good place to stop. Okay. Next class, we're going to continue on geometric transformations. We're going to use equations that we just derived to actually do not translating objects, but actually changing the reference frame. So the object remains in place, but now I change the reference frames around it, and I want to find the coordinates of those points in the new reference frame, okay, which is very related. And then after that, we're going to talk about color. Okay. Again, remember the first homework has been posted. It's due 1 week from today at midnight. Okay. See you Friday.